Professor Sassani is the chair of the technical activities committee. Welcome.
Thank you. Thank you very much. Hello, everyone. So I'm here as I'm the current chair of TAC. TAC is the Technical Activity Committee. So it's one of the standing committees of Rilem, which has the task of organizing, supervising the activity of the technical committees and try to solve possible issues that may arise. It has the task to approve new technical committees and overall supervise their activity. So among our activities, there's also the award of the Robert Lermite Medal, which is why I'm here today. So as you probably know, each year the Robert Lermite Medal is awarded to researchers that are younger than 40 years old. They are not necessarily already a member of the association, which is something important also to promote applications by young, promising researchers. So the requirement is that they must have had a very successful research activity, so they must have produced high-level research in the field of materials and structures. So for this year, we received a total of 24 high-quality applications from 10 countries over 4 continents. So a huge interest in this medal. Of these, 16% of the applications were for female applicants and the remaining 84 from male applicants. So for this year, the medal jury was composed by myself as the tax chair, by Professor Alexandra Bertrand from Toulouse as editor-in-chief of our journal, Rilem Technical Letters, as well as 2 experts appointed by TAC, José Duchel from Laval University here in Canada, and Professor Daniel Oliveira from the University of Avignon. So the 2023 Robert Lermite Medal was awarded to Professor Gaurav Sant, who is full professor in sustainability at the University of California, Los Angeles, UCLA, where he is the director of UCLA's Institute for Carbon Management. So it's a recurring topic, and we will hear in his presentation. So the Robert Lermite Medal was awarded to Professor Sant in recognition of his activity aimed at developing new technologies for carbon dioxide management and improving the service life of modern construction materials. In particular, he has played a significant role in development of carbonate cemented composites and data-driven concrete by application of machine learning. His remarkable research activity, which is testified by numerous indicators such as highly cited publications and patents, has reached beyond the borders of the academic community. In particular, it has led to the creation of award-winning companies and industrial consortia, and very importantly, he has also been very active in communicating the research results to legislators with the aim of illustrating pathways for technological carbon management. In 2017, Professor Sant received one of the Gustavo Colonetti medals for that year, again awarded by Rilem to researchers younger than 35 years old. And that medal was a recognition of his previous work on silicate dissolution in cementitious environments. So since then, Professor Sant has diversified his research activity, which has been accelerated since then, bringing him today to the leadership position in CO2 management that is today acknowledged by the Robert Lermite Medal. So I encourage you to give up an applause to Professor Sant. Now we will hear his plenary session presentation about the activity of the Institute for Carbon Management. So welcome to all of you.
screen. Yeah. The best time. So this is the see this error. If it doesn't work, we can just use the PDF. Oh yeah, it seems like it's not been downloaded. If it works, you can just try the PDF. You should be able to go to full screen on it. So, now you go to all the way to the full screen. Right. Okay. Hi everyone. Good morning. First of all, thanks very much to Rilem. Thanks very much to the jury. Of course, this is a very nice medal. Lots of people that I've respected very much over the years have all ended up winning it. So it's quite nice to actually have won it myself. I'm going to talk to you today a little bit about the work that we've done over the last 14 years. It's been 14 years since I started at UCLA. I'm going to tell you a little bit about the Institute for Carbon Management. It's sort of turned in, it was a hobby when it started. It's turned into an adventure of a lifetime. But before I go too far ahead, I'm going to start with telling you a little bit about myself. Actually, there we go. I'm going to tell you a little bit about myself. I grew up in India on the West Coast in a state called Goa. I lived in India until I was 18 and then decided to wander off to Indiana. I went to Purdue, I did a bachelor's, master's, and PhD. I trained with Jason Weiss. I finished up at Purdue. I went to EPFL where I did postdoctoral training with Karen Scribner, and I was hired by UCLA in 2010. I've been at UCLA for 14 years now. And it's been a wonderful adventure. There's lots of things that are wonderful about sunny California, other than real estate prices, but eventually learn to sort of deal with the pain. Over the course of this time, we've spent a lot of time sort of thinking about carbon management. And, it's something that we hear about in every forum that you can imagine, very, very mundane to very, very serious. And I've been really fortunate to work with a group of people over the years who are all faculty at the Institute, who work on sort of different aspects of this. And I'll tell you a little bit about the work that we do. But we were also very fortunate that UCLA allowed us to actually go out and create this thing. So we created the Institute about 5 years ago. And, we are in some ways a unique institute because we're a translational entity, and I'll talk about what that means as I go on. There we go. Okay, fine. So what does the Institute really do, right? So we are a carbon management institute, and I realize that these words are sort of heard very often now. But we're a translational institute, and what translational means is that we don't do any discovery research. So we've taken a position that's actually very, very opposed to discovery research, and it's focused purely on translation. And I'll talk about what we mean by translation in a second. But we work in two areas, and we chose very early on that we're going to have incredible focus around this. And the two areas that we chose is one is carbon management with a focus on avoidance, removal, and utilization of emissions, and a parallel area of focus on expanding supply chains and manufacturing pathways for the production of lithium, nickel, cobalt, manganese, and molybdenum. We intentionally chose these two areas because we thought that they are fundamental to the energy transition, and they are areas in some ways, which do not receive enough attention. And when we speak about translation, what we really mean is taking technology from the bench scale to commercial or pre-commercial prototypes. And so effectively, the way that this sets us up is you cannot take on a hobby project. If you cannot build a demonstration system that hits a scale of about 1,000 kilograms per day, so a metric ton per day, and I'll sort of explain why the metric ton is an important number, we won't actually work in the area. And so we've spent a lot of time sort of thinking about why we want to do this and how this actually happens. But really what it comes down to is really looking at a translation funnel. And so this is a process that we've developed, now over a decade. And it starts with the landscape analysis. Starts with the landscape analysis where we build a brand new team. These are generally people that we bring in from industry back into academia to study the landscape commercially, technologically, and in terms of how it actually looks today. we'll try and understand if there's any disruptive opportunity that we think could actually be accessed there. And we think about disruptive opportunities, what we're really focused on thinking about is there anything that you can do here that could make a difference in 5 to 10 years? If the answer is no, we drop it and we'll go on to something else. If we see that there's something interesting to be done, we'll go and do some validation of bed scale concepts, right? So one of the things that I've learned over the last 5 or 7 years is that anytime you read a scientific paper and you see data in it, very often there's hard questions around reproducibility. And so when you think about reproducibility, if we think that there's something interesting, we'll go back and actually re-examine reproducibility ourselves. So if all the bed scale concepts check out and we think that there's something interesting to be had, we continue expanding the team. So we build in more expertise into it. Lately, all of our work is really all done on process engineering, and I'll talk about why it's been process engineering. And then we'll start to run one of these crash development programs. I'll give you an example of a crash development program that we run, but we'll go into the actual translation funnel, right? So where we seek to essentially scale up, value engineer, and transform a bend scale concept into a functional system, right? So these are now systems that come out on the other end that run at a scale of somewhere between 100 kilograms and 10,000 kilograms a day. And I'll show you sort of scales of both. And this could be a variety of things, right? Could be devices, could be prototypes, could be software. And if we think that all of the technology risk has been retired, we'll put things into a startup company. So one of the things that we really focused on is that we need to have an endpoint to research. It cannot be research for the sake of research. And so commercialization has to be a pathway. So you have to pressure test it very hard. And if it all works out, it's great, right? Because what you might get at the end is something that's scalable, something that's cost effective, and that could be impactful. And of course, being in academia, we really like our prizes. And I'm actually particularly proud of two that we've won. We won the Carbon X Prize in 2021. We also won the Livability Challenge in 2021. And I think both of these prizes, made us really forced us to do things that were interesting to be able to win, which was quite good. So one of the things that, I would say my latest news, so to speak, has been this effort that we call aquatic. And it's really an approach for ocean-based carbon dioxide removal and hydrogen co-production. So this started as an interesting idea of, just doing simple electrolysis and seeing what simple electrolysis can do for you. It's taken on a life of its own, right? So this was something that we started working on in about 2018. It's turned into a company now. We've built pilot plants. But where we actually started in 2018 was all the way to the right-hand side of the screen. So just to give you a sense, those two containers that coupled bicompartment cell is approximately 6 centimeters in height. We went from that 6 centimeter cell to 2 pilot plants, one in Los Angeles, another one in Singapore, in effectively 24 months. That was about a 1 million X scale up in 24 months. And this is effectively what we look at translation be, right? How do you actually do pressure test this and do this in the real world? It sounds, in some ways straightforward. I will tell you it's the hardest things that we've ever done, right? In fact, it's hard because you need to make sure it all works, because failure is not an option. And the reason that failure is in fact not an option, and you need to sort of make your choice as well, is if you fail at a pilot plant scale, you basically wiped an effort for about 4 or 5 years, and you need to restart over. And so one of the things that we've tried to do is be really thoughtful about thinking, what are the things that we really want to ensure? These efforts are also incredibly expensive, right? So as an example, because of the way that we work, it's the way that we're funded with these really flexible funding programs, which come out of, don't come out of the equivalent of a National Science Foundation. So NSF, as an example, doesn't fund things of the sort. So you have to actually go out and create a funding base to be able to do things of this nature. But where it allows you to go is it allows you to go from something that looks like that pilot plant right there to something that looks kind of like this. So this is actually the latest adventure that we're on. So this is a sub-commercial technology demonstration. Again, it's an aquatic system, but it's an aquatic system that does 5,000 tons of carbon removal a year. And why did we choose to go out and do this, right? So this is effectively the minimum viable scale you need to be thinking about before you can assess whether something's actually going to work in the commercial world. So the scale of carbon management is so phenomenally large that there is no indication that something that's a success in the lab will ever work in the real world. And so if you need to create sort of this formative basis of confidence, it actually involves building things like this. So this is a plant that we're actually getting ready to build in Singapore. We're in the midst of engineering it right now. And this should be online in the next 18 to 24 months, fabrication willing, so to speak. So this is really what the Institute has been after. And the reason that we chose to do this, and we spent a lot of time thinking about really, is this the right model? Should this be done within a university? Is the university the right place for it? Actually, the answer turns out to be yes in a variety of different ways. Because as opposed to a startup company, in a university, you have sort of the freedom and the flexibility to really focus on a long-range outcome, right? So the problem is when you do things in a startup company, You've got investor pressure. You've got to be able to think about sort of what your employees want. There's lots of challenges for why it becomes really hard. If you take a step back and say, we're willing to bide our time, but do this well enough, you can actually do it within a university quite well, assuming the university lets you do it. So how are we organized, right? So we spend a lot of time sort of thinking about organization, and organization actually turns out to be a really important piece of this. But the way that ICM is set up is it's set up as a focused translational organization. And the reason it's set up as a focused translational organization is we were created to solve a technological challenge that cannot be solved within the existing structures of academia, corporates, or the government, right? So this intermediate scale does not exist. At one point in time, it used to exist in the US national labs. It's all drifted away. And so, we saw that there's an opportunity here. The next part is we're organized to be able to do work which requires very coordinated levels of engineering and system building, which again is an expertise that does not exist in academia anymore, right? In academia now, we really like publishing our papers, but building, as an example, of pilot plant is something that, as an example, at a tenure promotion, nobody really cares about, right? And that's an important thing. So it's really about incentive management. We wanted to do work that benefits society, and we all talk about benefiting society, but we wanted to be really tangible about it, right? What does benefit actually mean? How do you deliver it? How do you measure it? And measurement is really important, because if you don't measure impact, right, and you just speak about impact, it's actually very hard to be impactful. The last thing is, it's a question of organization. So we're designed in a way where we work with sort of a combination between a matrix organization and effectively a startup. Why? Because you need really agile decision making, and you need teams that are empowered. So as an example, we have a team in Singapore, we're building a new team in India. We need teams on the ground to be able to make decisions effectively that are appropriate to them, right? So command and control from Los Angeles does not really work. So how do you really have empowered systems is really an important question to ask. So where we've gone with all of this is we now created about 6 companies. They're all at very different levels of maturity. I would say some of them are sort of, I would say exotic hobby projects. Others are doing things that are really very real, as an example, right? So there's Carbon Build, which is the first one that we spun out. There's Concrete AI, which I'll talk about. I'll talk about these two as I go along. There's Aquatic that I just told you a little bit about the specifics, which is a very interesting lithium and nickel separations platform that's very much designed to disrupt how we think about lithium and nickel extractions today. There's XO44, which is, the 44 is for the molecular weight of CO2. It's a direct air capture platform. And there's Nextly Technologies, which is sort of the bet that we've made on cement decarbonization. So really a couple of things, as we think about why do we need to act quickly, why is this significant, why is this important? So fundamentally, there's a really slow rate of change as anything related to carbon management, right? It's something that we talk about a lot. If you actually go out and sort of look in the real world at large scale, what's going on, there's actually not a whole lot happening, right? I mean, the economic incentives simply do not exist. There's lots of issues related to amplifying forcing effects, right? So every incremental bit of emissions that we put into the atmosphere has a much bigger impact on the climate, and it's much harder to deal with in due course. We've created an environment of hype and hope, right? What this all leads to is, there's hype because somebody says, oh, I've done something really transformative, which is going to change the trajectory of climate change. Most often, totally untrue, right? Will never work, will never scale. The reason that this is important is effectively it creates asymmetric expectations. And this is actually a really big problem. And finally, we need really more successes, right? So if you look out into the landscape and look for true successes around industrial transformations, there's not that many of them. And fundamentally, I think one of the big things that we have to consider is that, every single one of us as consumers are responsible for climate change. But this is something that we've not really done a whole lot of, right? Really think about where does the responsibility lie? And how our personal habits actually contribute to responsibility. So with that said, I'm going to talk a little bit about decarbonizing cement production and concrete construction. This is obviously an area that I spend a lot of time thinking about. This room spends a lot of time thinking about it. And it's sort of my view of the world of where I think this is all headed. So I'm going to try and sort of skip some of the initial pieces. There's some slides here, but Professor Shah's covered them really nicely. So really, I think everybody knows, we're not going to live in a world without concrete anytime soon, right? Like going back to the caves or living in a tree is not really an option. Since that's not really an option, okay, we need to now do something about this. I think we have to focus on the fact that when you think about cement production, basically 65% of the carbon emissions are all embodied in the decomposition of limestone, right? Again, it's really well known, but you hear about ideas, we're going to use renewable heat, we're going to do something else, we're going to use an electric kiln. Fundamentally, if you do not deal with limestone CO2 emissions, effectively the plot is lost. And I think this is something that we fundamentally have to sort of come home to. So clinker production is really where the opportunity lies, right? Everything else you can argue is there's a pathway here, right? You can think about renewable heat, you can think about electric kilns, everything you can do something for, except limestone decomposition. And so that's both the challenge, but also the opportunity. Now, when you think about all of this, you also have to sort of think about the fact that one of the things that makes cement decarbonization really hard, and eventually the world thinks about dollars and cents a whole lot, converted to euros, British pounds, whatever else, Indian rupees. Eventually, it really comes to CO2 emissions on a per unit basis and per dollar of revenue. When you look at emissions per dollar of revenue, you basically see that the big issue that you have is cement simply is associated with very low revenue, lots of CO2. And that's what really makes decarbonization really hard. On the other hand, there's a reason why, as an example, Microsoft can go out and do carbon removal and they can purchase it, right? Because there's enough cash flow, there's enough profit in the business that you can do it. When you're looking at large commodity industries with low profitability, this becomes really hard. And so you've got to think about the economic nature of the challenge here. You've got to think about the cement decarbonization roadmap, right? So every industry organization in the world has some variant of this floating around, right? GCCA, PCA, the California Nevada Cement Association, whoever you wish, right? Effectively, I think there's a couple of important things to work on here. So number two is really important because there's a reduction of the clinker to cement ratio. This is basically telling you go look for SCMs. This is great. If you look at everything else, right, fuel switching is marginal, I would say, don't worry about it. Thermal energy efficiency, sure, there are some old plants around, but plants are generally running at really good thermal efficiency. There's electric energy intensity, but electrification, I would say, is marginal. Basically, the one at the top is really the problem, right? We've essentially chosen to use this catch-all of innovative technologies and hope that something is going to work, right? This is not a strategy. And I think this is really important because when you think about CCS or CCUS as applied to the cement industry, it's really, really, really hard to implement, right? And I'll talk about why as we go along. I think this is something we really need to focus on, but fundamentally, I think a really important thing we need to think about is really, are we affecting the emissions associated with clinker production? This is something I'll keep coming back to over and over again. So really, there's this question of what is carbon capture and geological storage, right? So this idea that you capture CO2 out of the atmosphere or the flue gas stream, whatever else, and you basically put it into a hole in the ground, right? It's something that we've done through the oil industry for about 70 years. I'm not going to comment on technical feasibility. Of course, everything has risks. Is the infrastructure available or not? Fundamentally, really, this turns into a question of cost. The simple way to think about this is really associated with the entropy of demixing CO2 from mixture of gases, right? So that's sort of the simplest thermodynamic way of describing it. What makes it really hard is that cement plants are generally not built on top of sequestration sites. And when you have plants that are putting out 1 million tons of CO2 a year, the question is, where do you put this 1 million tons of CO2 at a time, as an example, is a really big question. Sure, you can build pipelines, you can look for a reservoir, lots of things that you can do. They all imply big cost. And I think cost is something that we have to be really focused on when we think about cement production. I think when you think about the general landscape, and we've done this analysis looking at plants in India, looking at plants in the US, effectively more than 70% of cement plants are more than 100 miles from a geological sequestration site, at least 100 miles, right? And you've got to think about the fact that this is a long distance. This is not a short distance. And when you want to move 1 million tons of CO2 from a single plant 100 miles, poses some challenges, right? At the minimum, it poses some economic challenges. That said, should we consider the U in CCUS, utilization, right? So of course, I think we should consider utilization because if there's any opportunity to be able to reduce the total amount of CO2 you need to actually manage, if there's anything that you can do on site, you should absolutely do it. If there's anything that you can do in a distributed modular manner, you should absolutely do it. And so, we made a bet on utilization about a decade ago. We started working on calcium hydroxide carbonation because we thought that there was an opportunity to be able to produce carbonated cemented systems. Absolutely, we should do it. A couple of things to think about here is oxide composition is not everything. Kinetics do actually matter. And good measurement around thinking about utilization is also extremely important. This is, again, something that we don't think enough about. When we think about scale compatibility, right, and we have to think about scale compatibility a lot when we think about cement, effectively the industry today dilutes cement, as an example, with SCMs, right? So of course, these are, consider the fact that there are issues of codes and whatever else, but yes, there are SCMs and SCMs are continue to be a really important part of sort of the overall equation. There's a bunch of them available, right? There's fly ash, there's slag, there's calcined clays, there's all kinds of things around, and that's all wonderful. I think one of the things we really need to focus on is while SCMs are indeed a pathway to be able to reduce cement demand in the concrete binder, they do not affect the emissions intensity of clinker production. This is something we have to fundamentally get with. And what that really means is if you want to use SCMs to decarbonize cement production, we need to produce less clinker. And this has to happen, right? And at least my experience talking to a cement company, none of them sort of stands up and says, we want to produce less cement. Haven't heard them say that. There are two issues to this, right? So one part is really economic. I do not see corporations that have shareholders. It doesn't matter whether it's one family or 10 million shareholders as saying we want to reduce our revenue. This is number one. But number two, cement demand is going to continue to grow, and it's going to grow a lot, which means that we will need to produce more and more and more clinker. So it does not matter in the limit how much you choose to dilute it. You have to deal with clinker level emissions. There's no getting away from it. I think we need to be really careful about how we message this and position this, because replacing clinker by an SCM does not mean cement decarbonization. I think we have to make our peace with this. What it implies is you're diluting the cement content of the binder. You're not affecting the embodied carbon intensity of cement production. I think this is extremely important. Now, what all of this means is that when we think about cement decarbonization, while indeed SCMs are really important and we should continue to use them and expand our use of them, we have to sort of go back to the cement plant eventually and ask the question at the level of the cement plant. How do you actually decarbonize cement production itself? This is where eventually the plot gets thicker, right? We have to think about what makes cement decarbonization hard. Right? I think there's no escape from this. Eventually it's a commodity sector with a commodity mindset. You've got about $500 billion in capital assets in cement plants around the world. These aren't going to be turned off, right? We're not going to go out and build greenfield plants and say we're going to produce new cement out of greenfield plants. As an example, I often think about India. India is a place that we expect to be doing a lot of work over the next 2 decades or so. India produces about 350 million tons of cement per day. Production is going to quadruple over the next decade, right? So if you just look at the capex plans of every large cement company, India's going to produce a lot of cement, right? And if you think about the fact, you've got two opportunities here. Number one, anything that you can do at the level of the plant, cement plant, could make a difference. But you've got lots of capital investment that's going to go in, which is going to be a really important thing to be working on. I think what we want to really consider is that, the reason that I think the cement industry is a really big opportunity is it could be, in fact, an indicator for lots of other sectors. Things that we work with cement will essentially set a marker for what could be done with other sectors. And I think this is one of the reasons why cement is a really, really significant player for us to think of. Listen, there's lots of things that are hard about it, lots of things that are difficult about it. But if you can do it with cement, you can probably do it with most other things. Is a really good way of looking at it, right? So when you think about transformative decarbonization pathways, we did some work a couple of years ago where we went out and built this plot, and we worked on building this. So effectively, we took about 1 year of work, and all that came out of it was one graph. What we were really looking at is if you look at the incremental CO2 reduction, essentially going from 0 to 100%, what is the cost associated with that incremental reduction, right? Listen, there's some assumptions that underlie this. There's some analysis that went into it. And, you can ask the question of whether you agree or disagree or whatever else. But we looked at a bunch of things, right? So we looked at things from data-driven efficiency, so effectively concrete optimization, going all the way to CCS. It should be CCS at the top, not CSS. And we looked at a variety of things, right? In a lot of cases, the way you should think about it is the symbol itself shows the median value, and the range on the bar shows how much it could actually vary depending upon the pathway that you take. You can see for some of these things, the range is ridiculous, right? So we looked at even things like polymer binders. So what happens if you crack a hydrocarbon and produce a polymer binder? It's a really important question to ask. There's a lot of oil around, right? And nominally, you would ask the question, if plastics is a lot of binder, is there a way to actually create cemented systems, as an example, from plastic? So we went really, really broad, trying to think about what's going to create. What I'll tell you is that, in effect, while there's lots of things that you can do, we tried to sort of set our framing around 2 or 3 things, right? So the first thing is we wanted to focus on eliminating calcium carbonate's decomposition and focusing on what we could do at the existing level of the existing cement plant. This is number one. Number two, we wanted to look at process intensification by electrification. Essentially, can you electrify processes, right? So the more you can electrify, the easier things get, believe it or not, because electricity is a nice, efficient transduction, right? Also, if you don't need thermal heat, you don't need a fossil fuel. As an example, if you don't need thermal heat, you don't need to be able to move hydrocarbons around. So you've got something to think about there. The last part we want to think about is scale relevance and cost parity to OPC, right? And when I say cost parity, I mean cost parity on an NPV basis, so net present value basis, readjusted back to 2023 as an example. And really sort of keeping in mind this idea that we need to eliminate this dependence on CCS because you cannot use a one-size-fits-all solution, right? So saying that CCS is a singular climate strategy is not really a strategy, right? A strategy requires diversification of risk. And so thinking about that is sort of what went into this. And so what came out at the end of it is sort of, a variety of different things. And so if you look at this graph in many ways has sort of shaped our thinking on how we thought about approaching cement decarbonization, right? So the bets that we made were based on data-driven efficiencies, which I'll talk about, based on mineral carbonation, which I will also talk about, and based upon calcium hydroxide production, which I will also talk about. And sort of those are sort of the bets that we made. So I've said what was on this slide. I want to be a little bit mindful for time. And so I'm going to tell you a little bit about where we started with data-driven efficiencies, right? So the entire premise remains sort of focused on the fact that concrete production is empirical and experimental. So, I've always had this thesis that in general, that there's potentially an opportunity for better optimization at the level of a ready-mix concrete producer. And the reason that this comes about is I'm a third generation civil engineer. So I spent my childhood actually listening to people talk about building very large objects, right? And I heard my father talk about this all the time. Oh, you know what? We ordered an M20 concrete and what we got was an M10. We ordered an M30 and we got an M20. On the other hand, sometimes you order an M20 and you get an M50, right? And you really never know. And so what the M tells you is really telling you the compressive strength in megapascals, or 10 is a 10 megapascal, or 50 is a 50 megapascal. The reason for this is a couple of things, right? And I'm not sort of explaining anything new here, but really it's based on the heterogeneity of materials. Makes prediction of performance difficult. Number one, concrete proportioning is slow, empirical, and laborious. Even today, we use 3 and 4 point curves to come up with how we actually proportion and produce a concrete. And because of all of the uncertainty, you've got lots of duplicated safety margins across the supply chain, right? So now I can tell you, and I'll tell you this on the basis of data, we went out and curated data from all around the world. So we got data from India, we got data from Canada, we got data from the US, we got data from Europe. I'll tell you, in general, concrete is produced all around the world is over-designed by a factor between 20% and 200%. These numbers are actually real, and the range is in fact enormous. It's in fact almost hard to believe, but the numbers are actually really, really wide. You can actually argue that there's on average at least 30 to 40% over-design on a typical concrete that's produced. And when I talk about 30 to 40% over-design, I'm not talking about what is specified by the structural engineer. You've got the structural engineer that puts in a safety margin, you have a concrete producer that puts in a safety margin. You basically add the two up. That's the extent of over-design that you actually get. Listen, and all this comes down to is the sophistication of the operation. You've got a really sophisticated ready-mix producer, they've got tight distributions. These are about the best concrete you can get. Even there, you'll end up with 20% over-design pretty comfortably. You go to a poorly run operation, you'll see 50, 60% routinely. And we spent a lot of time looking at this, did a lot of work on trying to see if we could use an algorithm, classic data science, right? Machine learning, to be able to actually analyze these data sets, understand what the influential indicators were, and to actually be able to optimize. In effect, what it turns out as the optimization opportunity around cement is somewhere between 5 to 15% reduction. Obviously, has implications on cost. Depending upon the SCM palette that you have access to, you can reduce carbon emissions, effective carbon emissions in the binder, as an example, by somewhere between, give or take, let's say 10 to 30%. But where you actually see the important thing emerges, you can do all of this without compromising performance, right? And so we spent a lot of time working on this, came up with that. Concrete AI is now actually in production, in fact, and with ready-mix producers in the US and in Canada. And it's really a flexible optimization platform. That's all that it is. Of course, producers like it, and the reason that producers like it is it's all pure software, right? So capital cost is extremely low. All you've got sort of a cost associated with training people. And as long as you've trained people to be able to use the platform, it's all cloud-based, which is all wonderful. You can essentially have them do it in real time, right? And so you can do it at two levels. You can do it at the level of QC QA operation, but you can also do it where it actually directly feeds into a batch management system, where you can make actual adjustments in concrete, in fact, as it's being batched. The next thing that we spend time looking at is CO2 utilization, right? So the idea around CO2 utilization is how do you maintain CO2 within the same loop? And so the idea is pretty simple. You start with limestone, you take limestone, you burn it, you make calcium oxide. You go from calcium oxide, you slake it to produce calcium hydroxide. You carbonate calcium hydroxide and you go back to limestone, right? So limestone is essentially nature's original cementation agent. Can you use it for cementation was really the question to ask. Now, of course, this is not about running in circles. I'll tell you why in a second, why you in fact do need to go to calcium hydroxide. You can't actually carbonate calcium oxide. And we actually spent some time looking at this. Listen, the historical record is actually really long, right? So the picture that you see behind you is Hadrian's Wall. It's about 2,000 years old. An original example of lime mortar carbonation. So it's been around for a while, right? We know that this works. The question is, how far can it work and how effectively can you make it work? We spent a lot of time working on this. And I remember when we first started working on it, I still remember Fred Glassler and George Scherer. who I've got incredible respect for, and they've been right about nearly every single thing that they've ever said, saying to me, Gaurav, this is a really hard problem. And I said, if Fred and George say this is really hard, this is looking very bad. And for whatever set of reasons, either youth or stupidity, choose what you will, and persevered with it. Had some incredibly good students that worked on it. We realized that there was actually an interesting part here. In fact, there are two things to it. So calcium oxide does not carbonate really well. You form a pacillation film of calcium carbonate on the surface, you arrest the reaction, it doesn't work. Calcium hydroxide is an interesting creature because, in fact, what ends up happening is as you carbonate it, you've got a hydroxyl for carbonate exchange reaction, which produces water on the surface. The water continues to self-catalyze the reaction. So calcium hydroxide carbonates really fast, really effectively. What you're looking at here is carbonation, effectively extent of conversion as a function of time. You can get these reactions to run to near completion in 24 hours, even using 2% CO2. This is really quite important because at that point, we were really focused on flue gas. We were looking at, what is the lowest concentration of flue gas you could use. As an example, a natural gas power plant puts out CO2 at about 3%. We saw that there was a really good opportunity here, right? So we ended up going out to build this particular idea into a company. And where this all went is it ended up with carbon build, right? So carbon build is taking essentially concrete block and carbonating concrete block, doing it all at ambient pressure, ambient temperature using dilute CO2. And it gives you a significant CO2 reduction because you've got lots of utilization happening. And in fact, their first commercial plant went into production and is essentially producing and shipping block as we speak. Why is this significant, right? You can actually do it at the same cost basis as you do with regular block. In fact, when we first started to look at this, we didn't think it would happen, but we sort of said, let's see where it goes. It's often hard to tell. It actually does work. And again, for the market that this does actually work in, which is a market that contains a lot of fly ash, is actually quite nice because you can actually get a really nice CO2 utilization, and you've got something that actually appears to be quite scalable. So we'll see where the journey goes, but it's still early days. Now, an important thing to point out here is with regards to carbon build, the focus that we had was price, performance, and existing plant operations. Right? We managed to meet all of this, and in fact, we chose to make it a little bit hard for ourselves, but we chose for our initial customer to be a small family-run operation. Because we said, if you can do this at the scale of a small family-run operation, you can almost do it at any scale, right? So when it actually affects your own personal bottom line, you're going to be a lot more risk averse. And the fact that this actually worked is, I think quite a nice measure of that. The last thing I want to talk a little bit about is really calcium hydroxide. Right? So I've had a little bit of a fascination with calcium hydroxide for about a decade now, continues onward. The question that we had is really, can you produce calcium hydroxide electrochemically? There's lots of people that are trying, right? So there's Rilem, which is a company around which is trying to do this. There are others which are trying to do this. The question to really ask is, can you produce calcium hydroxide from solution? Can you do it effectively? So we actually had a DOE project that ran for a couple of years. We were trying to do this with a temperature swing. What I can tell you is temperature swing does not work. There's not enough waste heat around to be able to do this. So retrograde solubility does not help you. The good news is that there are other ways to do it. The question is, how do you really build a pathway to do it, right? So because we've spent a lot of time working on electrolysis, we chose to use an electrolysis pathway. Before I go any further, but let me tell you what sort of my fascination with calcium hydroxide. If you could produce it at a really large scale and with low carbon intensity, you can use it as a calcium oxide source for cement production. The nice thing about it is when you decompose it, you only release water. This is obviously wonderful. You can use it to make a carbon negative concrete. And this is actually really important because if you produce it at a low carbon intensity, calcium hydroxide will take up 0.6 units of CO2 per unit of itself. If you can carbonate it, calcium carbonate is actually cementitious. This is actually quite good. You've now got a pathway towards producing a concrete. The last part, which actually is really interesting, is that if you can carbonate calcium hydroxide, you can essentially use it as a mineral sink for CO2. So rather than thinking about geological sequestration, you can actually think about terrestrial surface sequestration of CO2, which is simply based upon a conversion of calcium carbonate. And so when you think about the fact that you've got sort of three ways that you can look at this material, there's actually quite a nice opportunity to be able to produce it if you could. The question to ask is there enough calcium around, right? So of course, this is a great question to ask. The short answer is yes, right? Of course, you can look at the easy stuff. You can look at slags and fly ashes and whatever else, and sure, there's a couple of essentially billion tons of calcium floating around in slags and fly ashes around the world. Sure, it's geographically localized, etc. But on balance, it's not enough. The real opportunity actually sits within things like basalts, right? And in fact, one of the reasons that we were drawn to basalts is because there's a lot of basalt in India. effectively the entire Deccan Plateau, all of peninsular India effectively is composed of basalts. There's enough basalt and aka enough calcium in India to support India's calcium demand for about the next 100,000 years minimum. And so this is actually quite a nice thing, right? Now, the good news is if it's beyond 100, frankly, I don't care. If it's beyond 1,000, well, it's looking really good. If it's anything beyond that, the world's your oyster. This is actually really important because you want to think about sort of geological availability. The question is, do you have the right alkalinity? The answer is yes. The question is, how do you really get the right reactivity? What reactivity, our solution to reactivity is really based on electrolysis, right? Why electrolysis? Assume a circumstance in which you've got access to renewable electricity. There's lots of renewable electricity that's coming available. It's probably going to be by far significantly available and localized because grids cannot actually move electrons around. And so if you can actually build plants where you've got stranded assets, particularly generation assets, this actually turns into quite a nice thing, right? So a good example, as an example, is the northwest of Germany. All of the interconnection lines from the North Sea actually come into the northwest of Germany. You've got terawatts of power available, which, okay, it's available only 8 hours of the day, but 8 hours of the day, you've got electrons that are never going to enter the German grid or the European grid, which in spite of being highly interconnected, in fact, cannot take those electrons anywhere else. So we think that the electrolysis actually has a nice sort of pathway here. Why? Take an electron at the cathode, you produce alkalinity and hydrogen. At the anode, you produce acidity and oxygen, right? Oxygen is good because hydrogen and oxygen allow you to do combustion if you wanted heat. But really, the fact that you can produce protons and hydroxyls is actually what you need to mobilize calcium in solution. You essentially take a rock, you hit it with a lot of acid, you dissolve it, you take it to a solution, you reprecipitate it out essentially as calcium hydroxide instead of being its native silicate, which is what it is as a disorder. So this is actually quite nice. And important thing to point out here, and I think this is really significant. Everybody, when they think about electrolysis, they think about every electrolyzer needing a platinum group metal, as an example, right? Everything needs iridium, everything needs platinum. Not really true. You can develop alkaline electrolyzers, which are in fact built on transition metals, things like nickel as an example, or manganese, and those actually turn out to be just as good as PGM-based electrolyzers, right? So keep in mind, when you're not purely after electrolysis for the sake of hydrogen production, in fact, the opportunity, what you can do actually opens up quite significantly. Of course, this is quite significant because, you have no CO2 emissions if you're using renewable electricity, and that's an important thing to think about. So we spent a lot of time working on this, thinking about it. We've gone out and built pilot systems, so we're in the midst of essentially doing a major scale up, but we've gone from something which is again 10 scale, smaller than this remote, to having a pilot plant that does about 10 kilograms of calcium hydroxide production a day. One of the nice things about it is, and I think this works, is the fact that in fact, right down here, we've been able to pick a pilot scale system. The nice thing about this pilot scale system, that's right, sorry, Andrew, I should have noticed that. The nice thing about this pilot scale system is it's already getting really, really close to this red line. So what is that red line? That red line actually shows the amount of energy needed to decompose limestone into calcium carbonate. What we think is important is to get somewhere in that vicinity. And if you can land in that vicinity, you'll actually be in a pretty good spot, right? Of course, calcium hydroxide is a little bit different from limestone. That number, the decomposition number is actually a little bit different because what you have is a material that decomposes at a lower temperature, not a higher temperature. But what we wanted to see is, could you produce calcium hydroxide at an energy that is approaching limestone's decomposition? We think that based upon lots of conversations that we've had with the cement sector, it seems as though that's a number that people really care about. And so we think that there's actually a pathway here. Lots of work to be done. And I can tell you, we've come a couple of orders of magnitude along this curve. There's a couple of more orders of magnitude to go. So we will see where it all ends up. But it seems like calcium hydroxide production might indeed be possible using just electricity. We'll see. In a couple of years, I might have a nice image to show of a plant that is being built. I'll sort of get ready to close this out. I know we've got a photo to go after, but I have a couple of things to point out, right? So cement is a strategic sector, and I think this is something that we want to try and focus on over and over and over again. Cement is a foundational material to society. We're going to use it to produce concrete. We need to have a pathway of being able to do it at a really large scale. While offshoring of production may indeed occur, and I think this is likely to happen in some markets, I think you will see that there will be border tariff adjustments that will make sure that you don't have leakage without an emissions cost being imposed. This is actually quite important. I think decarbonization is also going to be incented by strategic procurement. I think this is absolutely going to be the case. For example, California, passed, turned into law, SB 596, which essentially requires the cement industry in California to be carbon neutral by 2045. This is required by law, which means it's not a choice. And they are required to produce a 40% reduction in emissions by 2035. This is actually quite good because now you've got a reasonably large market. By US standards, California is a big market, it's about 10% of US production. And generally what happens in California ripples sooner or later across the US and across the world. I think this is actually a really good thing. But you're also seeing lots of interest, for example, from the federal government with these buy clean mandates, where emissions footprint is actually a part of procurement, right? So it's not only lowest cost, but it's also related to what's the emissions intensity of the material that you're buying. We think that there's big opportunities around renewable energy, right? So there's going to be lots of stranded electrons floating around in lots of parts of the world. How do we really use them? It's going to be an important question to ask. And big industrial processes could be a really big soak, so to speak, for renewable electrons. Last piece, before I go to the end, we need to really carefully ascertain if you're promoting CO2 avoidance, utilization, removal, or neither. There's some remarkably misleading work around. People come up with every LCA that they wish. The nice thing about an LCA is you can doctor it any way you want. We really need uniform, transparent LCA. This is really the need of the hour. We really need to distinguish between natural and accelerated carbonation, right? So I see the cement industry going out and talking about natural and ambient carbonation as this wonderful strategy of reducing emissions. Really concerning, right? I mean, it's sort of like saying, I'm going to pay you $1 million, but I'm going to pay you 70 years in the future. Until then, wait for the benefit. Listen, by no means am I disregarding the fact that concrete does take up CO2. But this is not a climate strategy. And I think this is really important to bear in mind, because net present value of emissions reduction, removal, mitigation is really what we're focused on, right? So if you think about it from a climate perspective, the atmosphere cares how much incremental CO2 you put into the atmosphere today. That's what drives the radiative forcing function. I think it's something which is important to think about. We should also keep in mind the CO2 concentration comes at a cost, right? So there's lots of work being done. As an example, people want to do carbonation with pure CO2. And I often ask the question, right? Have we tried to do a careful, just economic analysis? What does it cost to take CO2 from the atmosphere to 100% or from a flue gas to 100%? When you think about the economics, it gets really hard. And you realize that NPV, right, net present value parity, is effectively impossible to actually converge on. Something that we should really spend some time thinking about. Last part, which I think is actually being done quite nicely now, is that we need development and measurement methods for rapid CO2 uptake and reduction assessment, right? So thinking particularly about uptake, NIST has a nice working group, a nice committee, so to speak, that's been put together, that's been working on this to develop really fast methods for ascertaining uptake. And I think this is actually a nice thing that's being done. So really sort of going on to the summary conclusions, cement, concrete, and foundational materials, right? They're going to be here both today, tomorrow, and for a long time to come. We need to do a lot more work to think about decarbonizing cement production. This is really a once in a century type of opportunity. It's a generational opportunity. And I think, there's lots that we could be doing there. And while there's some work that has been done, there's obviously a whole lot more that remains. I think this is great because, in fact, this is where the journey starts. And with that said, I'd like to conclude and again, thank Rilem for this.